conditions. And the fabrication challenges are still there, and each and some or other time some new challenges are being cropping. Apart from that, the service related surprises are also awaited. So we don't know yet what are going to be the challenges that we have to address, especially with respect to the service related conditions. But as we say, when we try to do the incremental development, we will never reach the actual breakthrough development. So the necessity has already driven the power sector towards the inevitable change of using advanced grade of materials. So we are already in that segment, and we have to deal with it. So that is the real scenario. So I would like to start with sharing some of the experience with respect to the challenges in the chromoly steel segment itself. Um, uh, these are some of the persisting challenges that the power sector industry faces. Long and thick components, when it is made of the high chromium steel, it will have multiple number of joints to be made, especially for the heterostep kind of applications. When we talk about the higher chromium moly kind of steels, we call it the creep strength enhanced ferritic steels. These steels will necessitate the use of strict discipline, especially in handling and the fabrication. So the atmospheric control has to be very stringent. It will not tolerate like what the carbon steel does. And there may be a requirement of intermittent heat treatment, especially when we are talking about the thick section fabrication. We may not be able to complete it in one go, or in certain cases we may have to go for repair welding after intermittent or interstage examination. So when we talk about the intermittent heat treatments, we don't know how many heat treatments are allowed actually. So that is something which has to be seen. Even though thumb rule we say 3 heat treatments, but we don't know actually what is actually tolerable. And if it is 3 treatments are only allowed, and if suppose a condition comes, but the fabrication, then again it has to be manipulated in such a way that we are able to complete this entire fabrication with 3 treatments. So that is something which we have to really address. But currently the material is has been kind enough, and even though if it is more than 3 treatments, it is still tolerating and it is working fine. And we may have to go for the better inspection techniques, especially with respect to the tight cracks. And as I said earlier, service related failures have started to surface, especially these kind of materials are highly prone for a typical problem called the type 4 cracking, which occurs only at service. So when we push the material to that service condition where it is actually meant for, then these kind of defects, especially the welded fabrication, has started to surface. So that is something which we have to see how we are going to address. And this is one of the not a very new material, but of course it is newer in the Indian context. That is a T23 grade material, which is a chrome tungsten based material. What has actually we have observed is after the bend forming, a typical normalizing and tempered heat treatment is being carried out. But what has actually observed is what was actually observed. We ended up in having a poor toughness after we do this normalizing and tempering treatments. So then, as I said earlier, with the facility of WRA of thermophysical simulation called the Global Simulator, this has been simulated. And we have understood that when the cooling rates are low, some deleterious phases, especially the ferrite-based deleterious phases, are forming, and that is actually the culprit for reduction in toughness. So when we try to optimize the cooling rates, and when the cooling rate is crossing the critical value of 2 to 3 degrees per second, then we are able to achieve the required toughness, especially the impact property. So based on that, this tempering treatment, normalizing, the cooling after normalizing has been modified. And when we did that modification, we are able to achieve the required toughness properties. As you can see, the microstructural difference with when it is cooled at 0.5 degrees to 3 degrees per second, the change in the microstructures have actually resulted in the improved toughness. So that is what I was telling about the older materials. The challenges are cropping up every now and then, and that has to be addressed. But we are already into the advanced materials. So when we talk about the advanced material, there is a total shift. The cost is huge, exorbitantly higher, 10 to 12 times higher than the conventional material. So that necessitates a design optimization. We no longer have that freedom or flexibility to use the factor of safety at our will and wish. We have to definitely optimize to ensure that the cost is optimized. Then the higher strength austenitic grades. Austenitic grade is like a savior. Actually, I will be telling one or two experiences in the later stage. Whether it is really a savior or not, I don't know. Even though it is still go to consumable for solving critical problems or the belt related issues, we are going to talk about the higher strength austenitic grades, and it is going to pose different challenges. And the characteristic of the material is totally different. Welding behavior, of course, is also different. When we talk about such a strength and such ice temperature stabilities, then the forming behavior is also going to be different. So this is all the challenges that is going to be there because of this total shift. And the fact is, it is not known in the power sector. When we talk about these kind of materials, it is a common material used in the aerospace sector and defense sector, and in other strategic sectors as well. But when we talk about the conventional power sector, these grade of materials are very, very new for operation. So when we talk about the development, these are some of the components that have been developed, like thick pipes, headers, coils, valves, and panels. And the materials we have dealt with is from nickel alloy 617 740H, 82, Sanicro 25, 91, 92. And welding process development, when we talk about the process development, it add all the complementary processes or the supplementary processes as well, starting from welding with different kind of process, surfacing, non-destructive testing, bending, and heat treatment. So the one thing, thanks to our chairman, all the developments that have been carried out have been done on one-to-one scale. So when this development has happened, and as per the budget speech in the year 24, Honorable Finance Minister has agreed to help in setting up this advanced ultra supercritical facility, so it will be a reality. So the physical metallurgy of the nickel-based superalloys, it is highly alloyed. So it has two kinds of strengthening. One is solid solution strengthening, and the other one is a solid solution and plus the precipitation strengthening. So when we talk about the thermophysical properties, especially the quotient of thermal expansion, thermal conductivities, and so on, it is going to be between the ferritic steel and austenitic stainless steel. And grind boundary strengthening by carbides, but this is not very new. It has been happening in our chromoly steels as well. Highly stable at higher temperatures. So that is the thing that is being brought by these some advanced grade of materials. And when we talk about the mechanical properties, the mechanical properties are excellent in terms of strength, ductility, and impact toughness. And other than that, it also exhibit high work hardening behavior. So that is going to pose different challenges, especially when we talk about the forming studies. So when coming to the welding metallurgy of the nickel-based superalloys, it is somewhat similar to stainless steel. That when I say stainless steel, it is austenitic stainless steel. And but however, it is highly sensitive to impurities. It cannot tolerate impurities, especially the sulfur-based impurities. It will never tolerate, and grease, dust, and so on. The tolerance level is very low, and it is highly sensitive to heat input. So when I say this, it can lead to all kind of crackings, like liquefaction cracks, which is usually seen in any austenitic grade of materials. And then so we have to go for lower heat inputs based processes, and then stringent interpass temperature maintenance with any austenitic material welding. The interpass temperature between the adjacent between the two passes have to be controlled and maintained throughout. And another thing this nickel-based superalloys brings is the sluggish molten pool. The molten pool is highly sluggish, so that means it will not flow. So when it is not flowing, it will lead to the insufficient filling and can lead to cracks like crater cracks, and also chances of lack of fusion will become more. So what we have to do is we have to position the filler material or the molten pool in the area of interest exactly. So we will not have the flexibility that we were having in the conventional materials. And apart from that, it also has service related issues like strainage kind of cracking behavior, as you can see, which is shown on the right extreme. So the welding processes that have been used so far for the conventional fabrication: SMAW, GMAW, flash bud welding, induction pressure welding, gas tungsten arc welding, and submerged arc welding, we had wide variety of options that were available. So any material, the materials that were used in the conventional power plants, we were having options with respect to the material fabrication. But when we talk about these advanced grade of materials, the newer processes has to be adopted. So new process and technologies like arc wire, gas tungsten arc welding, one of the advancements that has happened in the TIG welding process. And so arc wire GTAW is used for 1G position for tubes and 1G or 5G position for pipes. Narrow gap welding will become mandatory because as I mentioned earlier, the sluggish molten pool will necessitate the positioning of the molten pool in the area of interest. Otherwise, there is a chance of lack of fusion kind of defects. So narrow gap TIG welding, that too with the arc wire for thicker joints. Tip process where the wire feeding can be automatic, and certain cases power beam welding process, especially when we are going to talk about the restraint joints with higher strength materials, the lower input process like power beam processes may be beneficial. So the industry is turning its eye towards this kind of processes as well. And enhanced degree of mechanization and automation will become necessary. And it is going to be a different ball game. And so different kinds of automation optimization will be required. So, as I said earlier, so there are various different kind of process that has to be used for the tube fabrication. So these are some of the tubes that have been used for optimize. These are some of the processes that have been optimized for the welding of tubes made of these advanced grade of materials. So arc wire triptych at the left extreme, where the wire feeding is automatic and welder will be maneuvering the electrode around the entire circumference of the tube for carrying out the welding. That is what we call the 5G position, or the arc wire GTW with the tube being rotated, that we call 1G position. And since we are talking about higher strength materials, conventionally the root welding is not done from inside, but this may need welding from inside. So this is the root welding of stubs, which is carried out from inside to ensure that its pressure and temperature withstandability is better. And of course, the orbital welding, where instead of the human maneuvering or manipulating the torch around the circumference, it is done by the machine. So orbital GTAW is something which we have optimized. And when it comes to the pipe fabrication, the narrow gap arc wire GTAW process, as you can see here, conventionally this grade of material is nickel based superalloy, which is having a thickness of more than 100 and this has to be welded and for some critical component. So that necessitated the use of this advanced process called the arc wire narrow gap GTAW process. um, as you can see here, conventionally when we want to weld these this kind of thicknesses, we produce or we prepare a edge which is having wider angles so that the torch is able to access the root. But in this case, it is welded from one side with a very narrow groove and having an angle of 2 to 6 degrees at the top, and we were able to complete with a single pass per layer. So so this I have said very easily, this is what we have done. As you can see here, we have done the optimization in 1G as well as in 5G. So 1G where the pipe is rotated, 5G where the torch is rotated in the narrow gap condition. This was said that easily, but the development really took the development had posed different challenges for us, especially controlling the deposition properly and especially avoiding the defects like the lack of fusion. So we have to do proper optimization. So the edge design or the joint design itself has been optimized accordingly to ensure we are able to achieve the penetration at the root from the top side, and we are able to manipulate and and oscillate the electrode in a proper way, that we are able to ensure that there is no lack of fusion kind of defect. So that is something which has been done. And you see on the right side the welded component. So as I said earlier, you can see the top width of the weld joint is very, very less compared to the thickness. So top width will be only 10 to 15 millimeters for a total thickness of component, which is around more than 100 millimeters. So, as I said, that is about the similar welding, but it will also need dissimilar welding combinations as well. Because when we talk about the cost optimization, one is the reduction in thickness, the other one is the use of the material, tailoring the material according to the requirement. So, as it is required, we may have to position these higher grade materials in that in the conditions where it is needed most, and in the other conditions where it is not required, we may have to go for the lower grade or lower strength materials, so that the cost is optimized properly. That is done from the engineering perspective, but when it comes to the manufacturing perspective, totally two different combination. When we talk about such kind of dissimilar combination, especially with the thicker sections, the heat treatment has to be different. So that is going to pose a different challenge. So what has been done is, so we have to choose a consumable which will be compatible with both the grade of materials, and that consumable has to be deposited by buttering, and where we deposit more than 20-25 mm, and then it will be individually heat treated according to the temperature requirement for that base material. Then the edge preparation will be done, and similar welding between the butter to butter layer will be carried out with the buttering consumable. And in that process, the after welding, the heat treatment is not mandatory. It can be done to reduce or alleviate the residual stresses, but it is not a mandatory requirement. And as I said, the chromoly steels is not new for the advanced ultra supercritical technology, but the higher chrome moly steel in the panel fabrication is something new which has not been done earlier. So there are various processes. Of course, GMAW has been conventionally used, but we have also optimized the laser based process, which is called the laser hybrid welding, where the laser, the advanced laser is being coupled with the GMAW processing. So both the process happen in tandem together. And the advantage is this is used for heat transfer. The tube is welded to a fin, and there have been challenges with the GMAW process. But one of the challenges with respect to the skip that is happening, some unwelded portion is something we call skip, and improper deposition and porosities kind of defect are something which we have been facing so far. And we wanted to also try and develop a newer process, that is laser hybrid welding. So it is like bringing the advantage of both the process together. So laser coupled with GMAW, we will be able to achieve the entire penetration from the top. When we use only GMAW process, we have to do the welding from both the sides. So we used to have 10, 12, 20 torch kind of machines where the welding will happen at both the areas, top and bottom, that is a fillet weld. But with the laser hybrid welding, the joining happens only from the top, and the entire and it will penetrate through and through the entire thickness. So the advantage is the one side welding, so reduce deposition, so reduce stresses. That is one thing. So for this kind of restraint joints, the cracking tendency can be reduced. And apart from that, it will also produce a high speed welding. So we will be able to increase the speed at least by 3 to 4 times compared to the conventional processing, where the speeds can in excess of a meter per minute can be achieved. And so that will improve the productivity. So the advantages it brings in, like the defect reduction, single side welding from the top to achieve the entire penetration, and good fusion characteristics, and the productivity will be better. And we have also attempted the laser based process, a joining process for welding of tubular components, especially which is in the laser regime. Like here also we have optimized the process for both autogenous as well as with the in the hybrid mode. So both have been done, and both have been proved. And laser definitely brings in advantages, especially with respect to the low temperature, low heat input fabrication. So the chances of defects like the cracking, especially the liquefaction kind of cracks, chances are reduced when we go for the laser based joining process. So this is what I said. So nickel is a material where we go to when we have a problem in weld fabrication. So we don't know. We thought it is going to be simple to do the art facing on a nickel based material. So we did that. So of course, this is something which we have attempted for the first time, where the internal deposition using the plasma arc welding to improve the wear resistance of the nickel based superalloy that is made. So here we have developed the process. When we did it on the plate, there was no problem, perfectly okay. But when we try to transform it into the actual fabrication in the tubular component, and when we did the deposition inside, we can see that it has actually cracked. So, so nickel is not something which is going to be behaving in the same way, especially when we talk about such constricted or restricted areas if we want to do the deposition. So again, we have to optimize in such a way that the kind of preheating has to be optimized and the cooling rates have to be controlled. And when we did that, we are able to overcome this issue, and this has been optimized. And of course, when we talk about such higher grade materials, there will be some design requirements where we have to go inside in the inaccessible location, or otherwise you have to go into a depth of say more than in excess of 500 and do a welding process. So that has been conventionally done with the Schiller metal arc welding, where the rod length is more than 400 so or more than 300 where the welder will be able to easily insert his hand and do the welding all around. But when we have to do such a kind of welding with the GTW process, it is going to be a difficult task. So when we talk about the advanced materials, we have to go for the better process like GTW process. So one such special purpose machine has been developed with the support by the Fronius India for the deep bore welding application. So we here the specialty is that it has a narrow torch which can go into a depth of 600 in excess of 600 and it can do the welding all around. And apart from that, the base is so designed that it will be able to preheat the component by resistance preheating as well. So that is something which has been done and has been optimized, and we could establish the process without any welding defects. And not just that, it is going to also, we are talking about austenitic materials, so all the problems that is going to be there with the austenitic materials, the inspection is going to be there with this nickel based superalloy as well. So non-destructive testing, different process have to be optimized. So penetrant, radiographic and ultrasonic testing. So what has been done is we have validated with the known defective samples, and based on that, the penetrant time and the developing time have been optimized within the code regulations, and with respect to the conventional LPA. And the coarse grained austenitic wells, we cannot use a conventional shear wave. So because of its high attenuation, especially because of absorption and scattering, we have to go for the angle based longitudinal waves, and that has been done. And of course the use of the phased array ultrasonic testing, so that also has been successfully established and ensured that all the fabrications have been tested by the advanced phased array ultrasonic testing, especially for the critical applications. And we have understood and we could optimize, and now we have the expertise with us to do the inspection as well. And not just with that, even with the radiographic inspection, it is not going to be the same as what we see in the case of steel because of the difference in the absorption coefficient. And the steel equivalent of nickel is 1.3. And the other problem what it gives is the nickel oxides. are difficult to detect, the oxide inclusions, because especially when they are thin, and most of the oxides in, especially with the GTW processes, are thin, and it will be oriented parallel to the surface. So there is a chance that we miss it. So that is something we have to take it at different orientations, and then ensure that the defects are not missed if the radiography is the only technique that is feasible. And of course, we talk about higher strength the material and work hardenable material, which gains strength when we do the work, when we try to process it, especially in the forming conditions. So the work hardenable nature of the material has posed the challenges with respect to the cold forming. So the capacity of the machine has to be enhanced. And not just that, as you can see on the left side, the computer based simulation has to be used as a tool to support and predict the behavior of the material when we talk about the different R by D ratios, so the radius to the diameter ratio. When we talk about, so we have to go for the computer simulation as well, and that has been carried out. Then the bend forming. So this is the incremental pipe bending, which has been done conventionally. This has been in practice, and we have been using it. But when we did it for the nickel-based superalloy, this is what we have observed. As you can see on the right side, it has cracked at the surface. So again, a lot of metallurgical studies have been carried out and optimization has been done, and we have also had a number of discussions with the material supplier to ensure and to understand the reason for these kind of defects. And so that when we have addressed the root cause, we are able to overcome this issue. And what I am trying to convey is, it was not a simple task at every stage. And heat treatment. So as I said, if the design engineer has to ask the flexibility, then the component shapes can be odd as well. And especially when we are going to talk about these kind of nickel based superalloys, the heat treatment temperature are also going to be different, so that we have seen the dissimilar welding as well. So the temperatures what is required for the nickel based superalloy is around 900 to 950 degrees centigrade, and in certain cases we may have to go for the solution annealing in excess of 1100 degrees centigrade. So the in situ heat treatment, one advantage, the thermal conductivity is not very high like in the case of the conventional steel material. But when we talk about these grade of thicknesses, in these grade of materials, we needed higher capacity facilities for the in situ heat treatments, and that has been done and that has been mastered. And now we know the winding of the coil on in what spacing it has to be done for what kind of configuration, so that we'll be able to achieve the desired temperature and for the entire soaking time, meeting the conditions of the code requirements. And apart from that, it is also we have to go for the temperature stabilities as well, so that also has been controlled. And we could establish the heat treatment for such grade of materials. And as I said earlier, in certain applications, when the combination of materials are so different, we will not be able to do a single heat treatment to cater to the requirement of the final application, so we have to go for solution annealing. And one advantage what these austenitic grade of materials brings in is the solution annealing will solve most of the issues. So that is something which we could do for three different grades of austenitic stainless steel. As you can see, on the right side, it has been heated to a high temperature and it has been cooled fast. So quenching has been carried out. So, to summarize, the newer generation material pose challenges in all the fabrication aspects. So, it can be and has been done or has been tackled with a better understanding of the nature of the material, appropriate upgradation of the facilities, using correct techniques, integrating it with computer and physical simulations. So that is all about our experience sharing in that high critical application. I will finish the presentation. I will take hardly 2 to 3 minutes where I want to touch upon the skilling initiative that WRI is doing in collaboration with the Ministry of Heavy Industries. So Ministry of Heavy Industries has recently sponsored a project for called Common Engineering Facility Center, the CEFC 5000, where we are been given with the responsibility of training welding professionals in huge numbers in excess of 5,000 year on year. So this is something which we have been doing all along throughout our journey. We can train anybody according to any code in any material at any level. So WRI is also into the PG certificate programs that we have been conducting 1 year PG program in collaboration with the PSG College of Technology in Coimbatore. This program is running for the past 18 years, and 19th batch is going to be recruited shortly in the month of June. It is a 1 year program. It is a PG certificate program, and the idea is to transform the fresh graduates industry ready, so that the industries will be able to rely upon with respect to their capabilities in the weld fabrication. So we have so far touch wood, all the candidates who have completed this program has been placed well. And coming to the Common Engineering Facility Center, WRI will not be able to cater to this 5,000, will be a huge number. So we have taken the support of 5 different units of BHL located in Ranipet, Haridwar, Jhansi, Bhopal, and Varanasi. And we have been working with the hub and spoke model, with WRI acting as hub with spokes as the extension centers. So this also helped WRI to fulfill its long pending dream of having extension centers in the country. So with this, we could at least establish the training centers in 5 different areas, some locations in the country. And we have increased our further upgraded our facilities. And so we have been doing the training at all levels, and these levels have been designed or developed by WRI from level 3 to level 6, where we can train the welding professional in any process. And these are some of the glimpses of the extension centers that are available or located at different areas, and already the training is going on in full swing. And with that, we have also further upgraded our facilities, and we have a new friction welding machine, the laser welding and cutting facilities, robotic welding machine. So this will not be used not just for training, but also for developing engineering solutions that is required for the industries, and helping them to adopt these newer processes in their fabrication. So that is with that. We could achieve in excess of 9,500 training so far with the support of the extension centers. So what we thought is a huge target, we could do that, especially with the support of the extension centers. So that is in brief about the capabilities and the experience with respect to the high temperature fabrications development that has been carried out at WRI. Thank you, one and all.
Thank you, sir, for your kind words, and really a very enlightening session for the participants and all the professionals. Everybody, we are confident that all will be. Now, sir, I request moderator, sir. Engineer K. Ravishankar
Yeah, I'm audible. Yeah, I am live. So I will just sum it up. First of all, it has been a very enlightening session by Dr. Shanmugarajan. So he just traced the entire boiler material history, right from the low alloy steel carbon steel material to the latest niche one, nickel-based alloys. And one thing I just want to submit, that I had the proud moment that I was associated with this AVC project, for which Dr. Shanmugarajan has talked about. And it was a very, very important development for the nation, because the AUC was a project which was guided by national climate change policy under the aegis of efficiency improvement and reduction of pollution of the environment, what he touched upon his opening remarks. So that nickel-based alloy development, especially for this AUC designs, were very, very appreciated and very, very involved task. And one point what he has noted, he had talked about in his brief this presentation, He talked about welding equipments availability and testing equipment availability in WRI, very high-end equipment. And then they what the studies they have done in weldability, NDT testing. And one of the things is consumable development. It's a very, very critical area. And for the niche development, niche application, WRI was involved in consumable development. And then two very, very important projects of national pride, joy, and self-reliance, Chandrayaan 3 and Pamban Bridge. The type of support was given by WRI. It is really commendable of the highest order. And coming to this presentation on the various materials, like one material I like to touch upon, this T23. It's a material which is still undergoing development and changes, still in court case, not incorporated in the ASME code of today. I was just going through some other document, is having a revision 10. And this is a material which was developed with very much of hype that it will have no post-foliar treatment, other thing. But today it has become, in the chrome moly range, it has become the most difficult material to fabricate with. Dr. Shanmugarajan will know, because so many process improvement, development, and changes they have done to use this material. Today, this material has become sort of a material which nobody wants to use. I'm very sorry to say. People who like to go with T91 rather than this material. So that is such a difficult material, this one. Coming to the nickel-based alloys, alloy 617 and 740H, it was developed for the AIUC application, as he told very clearly. So far in thermal plant, we have never used nickel alloy materials for pressure part. So it was a very daunting challenge for us to do the development. WRI has taken up the task along with our fabricating Trichy unit and Thermayum unit. We have developed the complete manufacturing technology for the tubes and pipes, taking the bending, welding, dissimilar welding of all combination what could exist in the AUC designs. It was developed successfully. Most important thing on a, not on a, I can say that prototype scale, but one-to-one. For example, we bought Inconel ID 280 mm and 47 thick, 5 meter, 6 meter length pipe of 740H, and we did the bending, one-to-one bending. So as if we have done the developments on the product level itself. So WRI has been actively very, very deeply involved in this development. And I am sure that participants today, they will take a cognizance of this development work WRI has been done, and they'll be in touch with WRI and for their own technical requirements. And once again, with these few words summing up, I congratulate Dr. Shanmugarajan for this encapsulating the total development work done by WRI in the realm of thermal plants. And I thank Institute of Engineers, administrative body, and senior members to have this sort of a session for the benefit of all the audience. Thank you once again for giving me this opportunity. I'm truly honored and humbled. Thank you so much.
Thank you, sir, for your kind word. Sir, in the question answer session, we are not seeing any questions in the dashboard. So, with kind permission from chairman of the division board, sir, we are going to conclude with a brief vote of thanks from our headquarters.
Sure, sir. I think question and answers can be taken through email from the participants.
Yes, yes. Participants can forward email to our email ID is there in the registration link. You can forward it there, and you can have the answer.
Yeah, thank you, sir. Thank you. Excellent presentations. We also, as an Institution of Engineers, also looking forward about some skill-oriented training program. In that regard, definitely we'll have a discussion in future. Excellent presentation, sir. Kingsuk, sir, please proceed.
Sir.
Please proceed.
Yes, sir. Good evening, everyone. We are now at the end of this wonderful webinar session. It is our pleasant privilege to propose the vote of thanks on behalf of IEI headquarters, Kolkata, for today's highly informative and engaging webinar on engineering solutions for high temperature and high pressure challenges in coal-fired thermal power plants. On behalf of IEI, we extend our sincere gratitude to the esteemed speaker of today's session, whose expert insights, practical experiences, and technical depth have greatly enriched our understanding of the complex challenges associated with the application of advanced materials, advanced welding processes, heat treatment, testing of fabrications and sub-assemblies, high temperature and high pressure operations in modern thermal power plants, etc. Sir, your valuable perspectives on skill development, improved design strategies, reliability enhancement, and safety considerations have been truly enlightening and beneficial to all the participants, sir. Thank you. We would also like to express our heartfelt thanks to the moderator of the session for his conceptualization and overview on the subject domain and summing up the proceedings of deliberation in a wonderful manner. Thank you, sir. We are thankful to the chairman of the Mechanical Engineering Division Board for his kind opening remarks and warm welcome address. Our appreciation goes to all participants, engineers, researchers, academicians, and students for your active involvement, thoughtful questions, and keen interest, which made the session interactive and meaningful. We hope today's deliberations inspire continued innovations and practical engineering solutions that contribute to safer, more efficient, and sustainable thermal power generation. Thank you, sir. And only one point, that our e-certification portal is open till tomorrow midnight. Those who want to obtain e-certificates, please follow the e-certification link in the flyer or scan the QR code. Certificates will be forwarded to the respective emails. Thank you all once again for your presence and participation. Thank you.
Thank you, sir. Thank you, sir. Thank you so much.
Thank you, sir. Thank you.